Alright, welcome back to Meteorology 101. I had to run that test. I was getting some buffer issues with YouTube warnings. So ran that for a little while. Looks good. I'm going to continue with the video. We're going to pull up the surface chart and see what systems are out there. And then we're going to get into the radar and see what's going on for any severe weather. So currently got all the data downloaded for the latest surface data. And here's the surface pressure. First I want to do, let's go ahead and do the station plots. Just explain this a little bit. Alright, so all the blue is marginal VFR conditions, and that is ceilings are between 1,000 and 3,000 feet, or visibility is between 3 and 5 miles. Any of the red, then the ceiling is below 1,000 feet, or visibility is below 1 mile. So basically, IFR condition to be 1 to 3 miles on the visibility, and then if we get a purple in here, that can be a low IFR, which is visibility but lower than a mile. So, and then the black is just showing the cloud cover. Any of these with 3/4 of the circle filled in or more is a ceiling. So half is scattered skies, 3/4 broken skies, and of course the full is overcast. So right now we have a lot of marginal VFR conditions in the south. Winds are out of the southeast. It looks like a little bit of rotation right there over Mississippi, and then got quite a bit of a wind shift over Texas, on eastern Texas, and then coming around to the north, and then from the southwest. So, and then even off the coast, we got some onshore flow directly pretty much from the east. So a lot of different stuff happening, but the southerly winds off the Gulf going into the Gulf states, that's just pumping moisture right into those Gulf states. So we'll go down there and we can see a couple areas where we have light rain is being reported for the observations, and actually up into southern Missouri looks like maybe a moderate rain in that area with lower visibility. So let's get this computer does the analyzation of these lines of equal pressure, the ISO bars on the surface chart, and places the lows. So we can always kind of take these lows with a grain of salt on the actual center of the placement. So like this one here, you can see winds out of the north, winds out of the southwest, and then winds out of the southeast. So you can see that rotation right there, and that low pressure should actually be pushed to the east just a little bit. So if this low is just pretty much what's left over of that whole low pressure system that was kind of pushing rapid around that high yesterday, with this ridge, this semi-permanent high pressure system ridging into the southeast. So that ridge is starting to weaken. The low pressure is pushing into it, and then it kind of wanted to break in two. So it's kind of starting to fill, and then staying close to the north. So would still expect with the high pressure further to the west and the high pressure off over the Atlantic, we got something's got to separate those two highs, because you have two highs next to each other. So you're pretty much looking at maybe like a stationary front or a frontal boundary right through that area. And then with those two high pressure systems kind of pushing toward each other, we got that boundary. We have all the moisture being pumped in from the south, and then the frontal boundary being the lift mechanism to create any lift that we might need for instability and the severe thunderstorms that we may get into the south. So right there's one station in western Louisiana, northwest Louisiana, reporting a thunderstorm right now. So that's on the latest download of this data. That's basically should be within the last hour. All right, so if we pull up the lines of equal temperature, we can see any thermal advection through these areas. So pretty much you have cold air advection coming out of the north, so that's going to give you lower heights, but the cold air pushes in and lifts that warm moist air, so creates that instability, and then creates any thunderstorms along that boundary of that advection. So with the semi-permanent high pressure system over the Atlantic, then we got the southerly flow, then we got the warm moist air, we got warm air advection being pushed all the way up pretty much almost into Tennessee there. So it's like all the way to northern Alabama, Mississippi, even into Tennessee. We see rain and we see those lower ceilings. So we got that warm, moist air just being pushed up and then pushed to the north and just creating all that instability. So we'll get into the radar and let's go see what we have for warnings. Okay, so there are no tornado warnings at this time, but we have several severe thunderstorm warnings and a few flash flood warnings, and then a few special marine warnings, so off the coast. So I would suspect most of that is down off the Gulf Coast. We'll get a wider view on this, pull up the national radar also, and then try to get a better idea what we got going on for the big picture. Give me a second to get that national radar up. Okay, so we got our animated national weather radar. We see most of that stuff is down over Mississippi, Alabama, going into Georgia. We got the line shooting all the way up, all the way pretty much south from northern Virginia. So, and then looks like behind that boundary, we have just scattered rain showers all through Ohio, pushing all the way to the southwest down into Arkansas. And then there are a couple of small areas of thunderstorm lines, those precip lines pushing through. So we'll have to get to the local radars and break these storms down and see which ones are being considered severe and if there may be any tornado threat there. So currently, this radar is in Mississippi. Let me get my screen centered here. Alright, so what do we got here? We got a tornado warning just popped up for Chilton County, Central Alabama, Eastern Perry County, and Central Alabama also. And that's until 6 p.m. Central. So about another half hour. So that is a new warning right now. And let's go see what we got going on right there. Let's download the loop. So all of the green are flash flood warnings. And then yellow are the severe thunderstorm warnings. Most of that stuff's to the south. And then looks like most of our warnings are through Alabama, Mississippi. Pretty much all through that line right there. And then some areas of hail being reported by radar, and then several reports from storm spotters. Looks like 3/4 inch of hail or higher. So I'll have to stop the loop. We'll get a look at that stuff, and then get a good look at this tornado warning. Let's say this tornado warning was most likely rotation indicated by radar, and that is it's a radar confirmed tornado. So let's go see what we got for radar confirmed. If we do a cross section on this area, let's see where that's really confirmed. Let's go to into the upper levels. I mean, it's not really extending into the upper angles of the radar. We got reports of wind damage, emergency managers out to the west of that. With this cross section across these higher reflectivities, I would expect to see a little bit more than that based on for a tornado warning. do a volume scan, see what we got for this cell. I got all the lower DBZs kind of shadowed out on this thing, the lower reflectivities, and you can see to the higher reflectivities. For some reason, the radar's not picking up or anything along the surface. We're pretty much 20,000 feet or higher. Base velocity. That is all motion toward the radar. It's all red. Do see some green. That's pretty much so it looks like holes in the reading there. So let's go on the surface and look at that. Alright, I'm just not seeing that right now. Let's go pull up the radar to the north of that and see what kind of readings we got on it. Get our download going here. Alright, so looks like to the north of the warning area we have more rotation, but this is pretty close to that radar site too. So any of that red's moving away from the radar, green's moving toward the radar, so definitely looks like rotation in that area. Let's go to the upper levels on that and see what we got for that rotation. Like I said, it's pretty close to the radar site itself, so you can get a lot of false information in that area. So if we have any rotation, major rotation, it looks like it definitely be way up in the upper levels. So there is the rotation. We could always get that vortex to reach the ground. So let's go back to the surface here, and then we'll go back to our base reflectivity, and then do a little hook echo right there. So let's see what we got. Pretty good rotation happening now. The higher reflectivities popping up. Let's go to the rotational scan. Alright, so like I said, most of it in the upper levels. Not much to the surface yet, but like I said, with that rotation, that could happen. That could continue to intensify and then push that vortex to the surface. So, like I said, the southwest quadrant of the thunderstorm cell is typically where the tornado happens. So, keep an eye on this one, see how it develops. But that's a pretty good little echo there. You can see your rotation. Now, if we go to the base velocity right there, there it is. So, radar site is just to the north. So we have, and we get out of that again. We got the red going toward the radar, green going away from the radar. I'm sorry, green going towards the radar, red going away from the radar. So you have that rotation in that area. So that's a pretty decent call, especially right here. There's that cell that's pushing, rotating right there. So the red out from the radar, green is in. So we're definitely rotating right around Clanton. So it looks like that's starting to intensify pretty good. Then we have a pretty good long line of thunderstorms all through Mississippi pushing through. They're actually that's all through in Alabama. So little cell over to the east, Hawkinsville. There's actually got a severe warning associated with that. That thing's pretty much dead. Nothing going on there. Once I go up about 2 or 3 degrees on the not even the we got 1.3 degrees on the radar, it's pretty much gone. So nothing on that one. Let me get my warnings window back up. So we got Shelby, Alabama, and Chilton, Alabama. It's a tornado warning. So here's another. This one is Shelby County. It's a tornado warning, and severe thunderstorm capable of producing a tornado was located near University of Montevallo, near Montevallo, moving east at 35 miles per hour, and it's a radar indicated rotation. So if we go into this one, So that's pretty close to that radar site too. So like I said, you can get a little bit of scattered stuff in there that just there's a lot of false information really, but I'm not saying this one's false. Let's just go break it down and see if we can do a cross section and see how intense this thing really is. So the radar is just pretty much cutting this off right around 20,000 feet, 15 to 20,000 feet. But we do have the high reflectivities all the way up to that level. Got a pretty strong updraft, so we're pushing pretty good on that. Let's go up to the upper levels. Let me zoom out. Go to the upper scans of the radar, and you can see how this thing thins out as they go up into the upper levels, but we still have high reflectivities well into the upper levels. So there's your hail right there. The high reflectivities, about 60, 65 dBZs, and we got 0.36 inches of hail, so just over a quarter inch of hail indicated by radar in that area. So we do a volume scan right there. Now we can see our high reflectivities. Okay, so now let's get a another breakdown on this thing because I want to see. Almost looks like a vortex trying to reach the ground right there. So I see a little bit of a rotation. We should see quite a bit of rotation right there. It looks like we got the storm tilt pushing up through here, and then that higher reflectivity is reaching just above 20,000 feet. So we're pretty intense on that. Let's pull up the rotation scan and see what it's got. Alright, we're definitely rotating in that storm. You see these little steps, that's just all scans from the radar because this thing's so close to that radar site that beam's just shooting out, overshooting out. That's why we're not picking anything up over this 40,000 feet. This thing's just right, the beam's at that level and then down. So, but like I said, you see the rotation all the way down pretty much to the surface. So we can definitely have a confirmed tornado at this site. Go back to the lower levels, all the way to the surface. And then we'll go right around that hail and do a scan on that, see if it gives us anything better. I don't think that makes a big difference on that though. See, we're still only 20,000 feet for the higher reflectivities, and we can still see kind of that rotation, that vortex into that storm. So let's get we can break this down a little bit more. We could take half of that red out of there, and then we can get more into the center of this thing and see what the structure of this thing is. So put the red back. We can actually put the orange in there if we wanted to. Do a complete volume scan. Let me get let's go do a complete scan on this thing. I'm gonna go down here where this, now we got a hail vortex indication down here in this the other warning right around Clanton. So let me get in that one. We'll see what's going on there. So we'll do a cross section right across there first. Probably a little long. Do a little short cross section. It looks like where our cross section is and where our radar showing is a little bit off because of that timing. Get back in there. So we got the reflectivities we need for severe thunderstorms in the upper levels. Let's do a volume scan on that one. Start seeing these little hooks. That's where we're going to get some activity. Right around that hail, showing those higher reflectivities too. That's going to be a good indicator of, once we get into them upper levels, how far that storm's going up, and showing those higher reflectivities. And then that's how that radar's indicating that as hail. Alright, let's go back to the surface and then pull up the base velocity, look for the rotation. We just got rotation all through that area. So this whole area right there is rotating. That's a pretty wide area. So you could have a tornado pretty much drop out of any of that at any time. But if you look at the closer, get rid of this, the closer rotation right in this area, that would be where I'd look for a vortex on the surface. Let's do a little scan on that. So let's go back, get a little bit wider area, and then we can pull this orange out of here. The orange is going to be from 40 to 50 dBz, so let's go up to 50. If we go up to the 50 for minimum, then we can see what the higher reflectivities and how far they go up. But if you look at this thing, it's like definitely got your horizontal rotation. That updraft goes up and then starts to come down, and then once you get a strong downdraft, and then you get wrapped around that updraft, and that could bring that vortex to the surface. So look at the rotation in this one. Alright, that's pretty good intense rotation all the way up into the upper levels, and that's pushing all the way up to 50,000 feet. So we're doing pretty good right there, and then that's reaching all the way down to the surface, right in the center of that scan, right over that cell. So probably definitely seeing something in that area. Definitely justifies this warning. So got possibility of severe hail. So the max is 32% possibility for being severe. That's severe hail is 1 inch or greater. Alright, so there's a pretty long list of severe thunderstorms, pretty much from Mississippi all the way through South Carolina, up into Virginia, North Carolina, South Carolina, Maryland. So pretty much Maryland all the way back. We're pretty much a whole line of severe thunderstorms in those areas, just that whole the whole East Coast. Let's go look at national radar again. Now you can see that line all the way through. Like I said, from Maryland all the way down through Virginia, North Carolina, South Carolina, all the way down. And then it looks like you got maybe some rotation right there at northern Alabama, and then maybe another little shortwave that's created right there in Alabama. So that's pretty much your rotation right there at your triple point. If you had just a small shortwave right there, that would be the rotation you'd look for right there in Alabama. That's where you're getting all the radar's picking up all that rotation and throwing those warnings. So let's get a look at this thing again. Alright, so everything's right there in central Alabama. Severe thunderstorms, 2 warnings. So, I mean, it pretty much lines up right there with that vortex. Let's get you back on the same page. So, like I said, right there through central Alabama. Pretty much lines up right there with that vortex. That looks like that shortwave pushing through. So, pretty heavy rain going through right now. They're getting hit pretty hard. Let's see what the spotters and anybody out there is reporting. We have, I don't think you can't see these pop-up windows. I got flash flood, law enforcement, water across County Road 87. The roadway is impassable. That's right near that radar site. Got another one near Maline, just east of Maline, and that is Shelby County. Law enforcement, 1 lane impassable at Butler Road and Big Oak Drive. One to the north near Pelham, flash flood, Joe Tucker Park, Shelby, Alabama, Shelby County, and the public reported flooding near county roads 52 and 95 in Helena. So if you're in those areas, stay out of that. You're not going to be able to pass them roads. And this continues on up to the north, just south of Hoover, Vestavia Hills, and south of Birmingham. So south of Birmingham, we got flash flooding downtown. Birmingham on the UAB campus near the intersection of 6th Avenue and 12th Street. Law enforcement reports residents being evacuated out of the Rue Mason apartments due to flash flooding. So that one's so deep that the apartments are flooding there, probably the lower levels. And then River Chase, Galleria, law enforcement reports all lanes of the Highway 31 at Highway 150 are closed due to flash flooding. So flash floods, flash flood. All the green through here is all flash flood warnings. Looks like one of our tornado warnings expired. And that was the one to the north. Let's go. Tornado warning for southwestern Shelby County is canceled. So that's been canceled. That was the one that was looking a little weak, I think, wasn't it? So we did a volume scan back on that. Yeah, that was down at the surface. But it did have some pretty good rotation all the way to the surface. I mean, there was definitely some activity there. It's just so close to the radar. Like I said, you can get a lot of false information from that. So and then the radar's just missing it. I mean, it's just so close to that radar, it's just overshooting it. So let's go to, well, let's get out of here. Another cross section, I don't want to do that. I want the volume scan. I'm going to go down to Maplesville. Keep an eye on that one. Alright, let's go find another radar to pull up. Let's see. There's KMXX. And that one's Maxwell Air Force Base. Download the loop on this thing. I get a little bit better picture of this thing. So up by that radar, we got the line shooting all the way into that radar. And KBMX, but we got almost 1 inch hail, 0.99 inch hail indicated by radar. Now just updated to a ½ inch in the back behind that line, that thunderstorm line, and we got 3/4 of an inch just inside that tornado warning. So high reflectivity is just outside the warning area. So let's go scan this thing. Definitely look like some rotation on that. Do the rotation scan, see what we got here. So definitely rotation in the upper levels here also. That's pushing all the way up above 40,000 feet. So good indication right there. Let's go down here to this cell, see what we got. There's no, it's in a severe warning, it looks like. And then the higher reflectivity look a little more elevated, or the radar is just missing those lower levels. So alright, let's see, all in severe thunderstorm. Well, that whole line is just severe. So you can get a tornado warning pop up anytime in any of those areas. Once it starts, that radar starts indicating rotation, you can have a tornado pop up anytime. So anytime you're in a severe thunderstorm, you're looking at 1 inch hail, 58 mile per hour winds, and or possibility of producing a tornado. So that's the severe criteria. You can see a little bit better formation than that, but that's doing pretty good. I mean, that's a pretty strong cell. See if I can get where I'm not cutting that thing off. My radar scan's a little ahead of me, I think, for where I'm actually picking up the 3D scan. I think the radar is just one shot ahead from where this is. The 3D scan can't catch it yet. So look at the velocity on this thing. Now let's get to the other side. We definitely got rotation all the way up in the upper levels at 50,000 feet, and then rotation right there at 20,000 feet. So we could definitely all through the center of that storm. Let me see if I can get rid of some of that green. See what this does. I think I'm getting rid of pretty much everything. Let me go. There you go. That's a little better. Now we can get a better vertical look at this thing and see our rotation. So if any of the green colors are going in toward the radar, red's going out. So you can definitely see we have rotation in that storm just on the base velocity. Now we can just click the rotation volume scan. Now you can definitely see our rotation pretty much all through every level of that storm also. Alright, go back to the base reflectivity. High reflectivity is all the way up to above 30,000 feet. So definitely capable of making hail, that's for sure. Alright. Gonna play that loop. So we did get another severe warning pop up just ahead on that last scan. And that one is severe thunderstorm warning for Coosa County and east central Alabama until 7 p.m. Central Time. Getting ready to do another update here. It's on the latest latest scan, so pull up another volume scan down here. Now we cut out the that base velocity, make it a little more transparent, and I just don't see too much red on that area. So I think this is outside of a warning area anyway, so we don't have the rotation we need. That was well to the south, but it did have the so 0.63 inches of hail, just over ½ inch of hail, and through that cell, and that just moved with it. So we now got almost an inch of hail to the south of the warning area, and then the hail 0.63 inches there, and then we got that vortex signature right there. So let's see what we got here. It's saying a threshold 8.0 and 6221 feet and it's 4258 feet. I'm not sure what that means on the radar. I'm going to look up this look that up on the program, find out what that means. And then 3/4 inch hail pretty much to the east. So let's go do another scan on this area. Pull up the velocity. So the base velocity is going to show us ingoing and outgoing winds from the radar. So when you get those right on top of each other, you can, like cutting this into a 3D, you can actually see the rotation throughout that storm. So that's pretty intense rotation all the way to the upper levels on that. So get a better look at this thing. That one's pretty much gone. Okay, there it is. Maybe I'm one scan behind. Let me go back a little bit. Still cutting it off just a little bit, but you can see definitely rotation 25 to 30,000 feet. So trying to bring that down to the surface. And we do have the strong winds there, but we don't. Let me go do a. Let's go to the upper levels and see what we got. Upper scans of the radar. So we're pretty intense about halfway up. Once we get up 4 degrees on the radar, then it just pretty much disappears. So got the rain started in southwest Ohio, if you can see the through the other camera. Let me see if I can adjust that picture for you too. And it's going to shut me off here in a minute. let's go to I don't know if it's gonna let me or not. Alright, it's just gonna try to shut me down. Alright, see if we can bump up the, drop the contrast, maybe try to get a better look at them clouds. Brightness. That's pretty much it for that. So, I mean, I did get into, you can actually see the cloud structure a little bit better. Not picking up the rain or anything, but see what we got going on in Ohio. It was raining. Let's go see what see what's on the radar. Okay, we got some pretty strong cells down in Kentucky, and then southwest Ohio. We got, this is the stuff moving through right now. This is where we're at, right around Batavia. So we have this some isolated stuff. We got a little bit of stuff to the south headed into Bethel. Let's play that loop real quick. Alright, so that's cranking through pretty quick, so let's go look at that cell real quick, see what we got. Do a cross section on that. See if we can catch some of those higher DBZ, see where we got for high reflectivities into the upper levels. We got a little bit of tilt on that thing, but you know, no major threat. I mean, we're not even up to, we're barely touching 10,000 feet right there at 40 DBZ, so 45, I mean, I wouldn't, nothing to be concerned about here. And then do a volume scan on a small cell like that. I mean, it looks like the little bit of curvature to that storm, but like I said, nothing nothing even to be concerned about. Let's go we can put pretty much everything back into that, and then let's do this real quick. We can bring this thing to the different reflectivities, show you the height of the storm, 20,000 feet for the lower reflectivities, and then getting into the higher reflectivities, we're all the way down, you know, well below 10,000 feet for 50 dBz, so we don't have to worry about anything being severe on that level. So we can just build this storm from the bottom up. And that's pretty much it. I'm all the way maxed out right there. That's why it disappears. So let's get a top view of that thing. You see the structure of that storm. You see how it's built up all the way up there. So, you know, like I said, nothing significant in this. Not even filling half this block. Let's go back to we'll go back to the south. We can do that with some of those severe storms We're just really nothing going on here. Here's a stronger area just to the east, and then that's our strongest point. We're about 15,000 feet for the tops of that thing, so really nothing to worry about there. Let's go back. Drop to the higher reflectivities. I mean, like I said, there's nothing there either, so you see that storm build from the bottom up. Alright, so let's get out of there. There's one to the south. This is down in the just north of Frankfort, Kentucky. A little bit of it's a ripple there. It might be just that. All those ripples might be from the radar scan. So if we look at this one from the bottom up, got a little bit of reflectivity, higher reflectivity right there, just about 10,000 feet. So I mean, that could, if it was a lot bigger than that, I'd say, you know, watch out for that becoming a severe thunderstorm warning. But it's just not even there, so just not enough volume to worry about. So, then your tops are shooting up to about 30,000 feet, and then, like I said, it's pretty rough because of that radar scan. All right, let's go get rid of this thing. I'm gonna move this radar around. Gotta make sure I click on my pointer to do that. All right, so here's a little bit of hail, showing 0.36 inches of hail, just southwest of Shelbyville. Let's get a volume scan on that. Now you can see a little bit of overshooting tops, 30,000 feet on this thing. That's pretty choppy too, so that could be part of that radar scan. And then we're just showing lower reflectivities at this point. So that being all hollowed out like that, it's only showing one reflectivity value. So if we go up to the higher reflectivities, we go up to 50 dB zoom, and that's just pretty much almost disappears. And then we build it from the center out, and then you can see your lower reflectivities on the outline of that. So your core is mostly green, yellow, orange. That just fills in the center. It's only doing one reflectivity at a time. So then you get up to these lower reflectivities, 10 to 15 dBz, which is really nothing. And then that shows the outline of that cell. So pretty much that's it for that. Let's go to back to the south. Back on all of our warnings here. CamXX. Download the loop there. Alright, like I said, we can see our line now. Let's go back to our warnings window. We have no tornado warnings. About 17 or 18 severe thunderstorm warnings. We got about 6 flash flood warnings and 8 special marine warnings. So see where they're at. What do we got for? There's a special marine warning over here. They're all off the East Coast, pretty much all in through the inlets of right around North Carolina. So severe thunderstorm, North Carolina, south through South Carolina. Pretty good little cell there in Georgia, but nothing severe. We got a flash flood warning to the north. And then, like I said, everything's back in Mississippi, Alabama. Pretty much Alabama. Everything's in Alabama right now. Alright, so let's go get a look at, here's a higher reflectivity, a little curvature. Let's go to the curves of this thing and try to find, here's some pretty good 3/4 inch hail. So let's go into that cell and see what we got. See if we can build that cell to a from the bottom up. Go to the higher reflectivity. See 50 dBz's right there. That's where we can be severe. If we're 50 dBz at 10,000 feet, you can go severe. So this one's definitely rates to be severe. It's over 20,000 feet, pushing almost 30,000 feet with those reflectivities. So it's pretty good rotation right there. Pretty good reflectivities in the upper levels. It means we got a pretty strong updraft. So if you got, here's the rotation all the way through. So that storm's got rotation all the way up to 50,000 feet. So throughout that storm, so you can have a vortex pop out of that thing anytime. Get the base velocity and pretty much cut out all the red there. Let's see what we got going on here. Trying to see if we have any red pop up at any level here. I don't really see anything, so that's why there's no tornado warning right now. They're just not seeing the rotation and the velocity. All right, let's go. Let's get back in there. We'll just see what this look like from the reflectivity standpoint. Let's go all the way up. Lightest reflectivities, overshooting tops almost to 50,000 feet. And that's a pretty thin for lower reflectivity. You see, it's just a blanket up there. That means when you get into the center of the storm, it gets more intense. So as we pull up from 10 to 15 dBz, now you can see a little bit better structure of that storm. And then 15 to 20. We're not into the severe range yet, but we're you can see those updrafts, how these lower reflectivities are wrapping around the higher reflectivities in the center of that storm, so showing that structure. Right there's about your strongest part of the storm, where the updraft is. And then let's bring us down to back to 50 dBz. That's pretty intense. Anything above 10,000 feet is severe, and we got we're well up above just above 20,000 feet. So, and then going up from 50 to 60, really nothing there. There's a little tiny bit of 60 right there. You can see that, and that's actually just above 20,000 feet. So pretty good. I mean, just a little bit of, definitely there's higher reflectivities. We get up to 60, 65, 70. Start going up to white and stuff. That's I guess a pretty good size hail at that point. So this one just a little bit of hail. I think we said what 3/4 inch was showing on radar. So pretty much it. Now we can build this storm from the center out. Let's get a little angle on this thing. So you can't really see the purple. It's in there. Then it goes to the red, orange, yellow. Now you can see your updraft right there popping up. Maybe zoom out a little bit. Bring it back down. And then our lower reflectivity is going well into the upper levels. And we're pushing almost 50,000 feet, so that's a pretty heavy duty updraft pushing up that high. So, all right, well that's pretty much it for that. Let's go. We'll keep an eye on these warnings. I'll leave the warning window open where I can see it. If we get a tornado warning pop up, we'll come back over here. Let's go. Let's go play with the charts a little bit. See what we got going on. Alright, we got low pressure over the Great Lakes region. Let's throw the computer generated fronts on here. I hate doing that because they pretty much suck. They're like we got rotation here. We got, well, not really. Let's see. We got easterly winds, southerly winds. I'm looking for a wind shift. Right there's one. So I'm going to see if I can get a display up. Let's go do a let's do a drawing on this thing. Get my See my system up here. I don't know if you can see that little window or not. Looks a lot darker than it really is outside. I think I pretty much screwed up that contrast, so I'll have to readjust later. Grab my pen. Let's see what we got going on here. So, all right, like I said, we're looking for wind shifts, temperatures, dew points. There's several things you can look for frontal placement. So when you see a wind out of the northwest, one shifting back out of the southwest, you get that shift. That tells me there's a boundary right there. So we got one here, convergence right there, winds there, and then we go southerly, northwesterly, northerly. So you look at this high pressure, winds flow clockwise around the high, and they'll flow out of a high. So you'll kind of get a wind pattern pushing out of the high. So if you see anything on the surface that looks like, okay, we're going, they don't follow the isobars on the surface. So you got winds going along the isobars and then they're pushing out. So you're in that's a high pressure system where the winds are pushing out of that high. All right, so let's go to our wind shift is what we're looking for right here. There's the wind shift. That's just lower level convergence right there. What's over Texas? So we didn't really have any severe weather over Texas. This is probably about an hour old now, so maybe a little bit longer. Don't see anything at that station. A lot of these stations are calm winds or light, very light winds. There's really nothing popping up because of you just don't have the got the contours are so far apart. If I would look for rotation around this low to prove that low is there. It's calm winds. We got a southeasterly flow. Here's a shift maybe right there. Let's see what we got going on there. Winds are going that way and this way, so it wouldn't really count that too much as a shift. Let's go 58 degrees, 69 degrees. That's a pretty good difference right there. 66 degrees, and then what is that, 80? Is that 80 degrees? We definitely got a good difference right there. All right, so low pressure system. Here's a trough. You can see a wind shift right there, right out of that trough. Here's a trough over here. So we're looking for a wind shift here for the warm front. I don't really see much going on. Okay, here we go. We got one out of the northeast, one out of the southwest. All right, so looks like possibly our warm front would be. Here, let's go with the right color here, real quick. Out of there, right there, any warm air advection, but it's very weak warm air advection. But if I had to place a warm front, it'd probably be right around that area. Now, with our wind shift here, let's bring that cold front out. And then, like I said, with our temperature differences, we had 66, 80. We'll definitely bring that front down through there. We got 79, 69. So bring it around there. And then you're pretty much going to bring it right around that high pressure system. Really not a lot of advection in this area, but I'd almost have to go with that shift there. I mean, we got temperature differences. I mean, it is definitely a cold front, so just to keep it cold. I don't like doing that in areas where there's isobars or there's really no predominant trough, but we do have that wind shift, so we can't really argue with it too much. That is definitely a trough right there. So we can almost probably close this low off, take these isobars, come down like that, and then this one's probably close off like this, and then we can bring down. We'd have to analyze all the pressures to do that. That takes some time, but I might do that one day, just analyze a surface chart from scratch, just throw up the surface plots, analyze it, and go from there. But we got, right now, like I said, I was like trying to get my red going here. Maybe with the warm front, got to color those in on the surface. They're hollow on the upper levels, so we don't want to confuse anybody. A little bit messy drawing there. And the blue, bring it down through the shifts, back behind those warmer temperatures, in front of those colder temperatures, around those wind shifts, and then bring that cold front right around that high. So kind of place that frontal system right there, if that's my initial guess. So looks like got a ridge that had to be a trough right there, and maybe some ridging up here, and then be an inverted trough right there. We definitely got our ridge all the way down into Texas from the high pressure system. So let's go. We can throw this computer generated fronts on there, just see what we got. Let me go to alright, so I brought down the warm front. This thing went cold back into warm, throwing low pressure systems all through that area. Like I said, if it did anything with that outside of a cold front, I would say stationary. Just come stationary right out of that. A little bit of cold air advection right out of that low, and then maybe going stationary because the isobars are so far apart and there's two high pressure systems. You gotta have something to separate those highs. If it ain't a low pressure system, it has to be a stationary front. Because the winds should oppose each other more. So that's why I kept it a cold front, and then based on those temperatures. So if we had another little area shortwave developing right there, then you could go stationary into a warm front. You have to prove the warm air advection head of that front, and then back out with the cold front. But I bring that cold front back around, right around that high pressure system. So they're dropping a little bit further south. All right, so let me get a drink real quick. I bring that cold front back around. Now this low with that inverted trough, we maybe have a low pressure system developing over just close to that Four Corners area. That's pretty popular this time of year. Maybe a cutoff low reaching to the surface, but we'd have to get in the upper levels to find out. Right now, it's just cold front wrapped around the high, right at the leading edge of that ridge. The temperature difference, the wind shifts. Look at the placement of that. Now, if this trough, the prefrontal trough, definitely got the ridging off the subtropical high. So semi-permanent high pressure over the Atlantic, ridging all the way up into Florida, and then just pumping that warm, moist air off the Gulf right up into the Gulf states. And then if you have a major, minor little shortwave, just a troughing, a little bit of troughing right there. You can see these the wind directions are shifting right here. One's going from the southeast, the one's going from the southwest, and then that's the low-level divergence in that area. So that's probably why this one reason this computer's placing a high there. But you start getting, let's get this cleared up just a little bit. Get back into this draw mode and try to pull something here. Let's see. What we gotta do is we gotta prove rotation. So if we had that trough in there, so here's rotation right there. You got the winds out of the southwest, winds out of the southeast. Now we have that rotation, so we could definitely put a trough right there. So now any of that warm moist air pumping under this thing, and then you got the instability with the trough, that low pressure or stationary front, or even a cold front. Now you have your lift. So now there's all of that, every ingredient you need: moisture, instability, lift, to give you all the severe weather you need right there. So as we're everything's right there in Alabama right now. We can see that shift. So we can see that rotation. So there is where you're looking for most of that severe weather, and that's where it is, right there in Alabama. That's based off the surface data. Okay, so a lot of other things to look for on surface charts. So I mean, it's like if you go, here's a 12, here's a 14, 16, 18. Now you look at your isotherms, and then you get your isobars wrapped around here. So now you're getting, they start crossing each other. Now you got your cold air advection, warm air advection, and then you got a, that's a 12 degree, 14, there's a 12. So that's a cold pocket right there. So cold core high. Pretty weak on the core, but it is a cold core high. It's a cold, it's a continental polar air mass dropped down out of Canada. So cold core, you get that cold air coming through, and then it dominates. It's a higher density of the cold air, and I'm gonna make that blue because cold is blue. So denser air that stays on the surface, pushes through, and then any of the less dense air, more buoyant air, pushes up above that cold air as it pushes through. Now, once that you get into an area like down here where the instability is, you get the lift from the front pushing through. Then that picks up that moisture, instability pushes it up, and then once you can go to a Shelby chart, find where your level of free convection is, and once you hit that level of free convection, that storm just goes wherever it wants, goes as high as it wants. The updraft pushes past that point all the way to the tropopause. Then you get the overshooting tops, and that's why we see these storms in Alabama shooting all the way up to 50,000 feet. So, all right, I'm gonna go with our main features are going to be the high, the low, I'd say a cold front. We got that warm front, and then maybe a prefrontal trough. I don't have the black lit up to show like a prefrontal trough right in this area. So there's your main features of the surface chart. All right, so this trough, maybe a low is trying to develop right there. Still high to the north. Okay, so as we watch this high pressure system, we watch that low pressure system, and we watch this low, maybe just a short wave pushing through. Let's keep an eye on that. And when we go to the models, we'll see if that's going to develop. That's going to be later, though. I'm not going to get to the models just yet. So let's go to the 850 millibar chart. We're going to go up to about 5,000 feet. Alright, let me go. Build an 850 with moisture. We're going to show moisture, the upper level contours. Lines of equal pressure in the upper levels is lines of equal height. Those are called contours. Still isotherms, lines of equal temperature. We're going to show 60% humidity or more, showing all the green. Anywhere there's 60% humidity plus, we can have precipitation, or we definitely got cloud cover. And then they'll show our station plots. Now, I'm going to go ahead and, let's see. I think we got enough station plots on here. We may be able to get a little bit more. Let me bump up the density. Always got lighter density in the upper levels because there are only so many weather stations across the United States that launch the balloons, the radiosonde balloons, and then this data only comes out every 12 hours. So any of these charts are going to be anywhere up to 12 hours old. All right, so I'm going to erase this real quick, and we're just going to do that one more time so I can get the most data plots on there, because when we want to analyze these charts, we want to see how much data, the most data we can see in these upper levels, so we can place those, any upper fronts or those features. We want to see how well they're developed in those upper levels. This down here, oh crap, I'm not even, let me get in drawing mode. I'll wait till this is finished. We got plots coming up. Okay, so let me get in here and get you back on the drawing mode here. Okay. All of the green is, like I said, 60% humidity. This is kind of putting a hole there because it sees that blank station. So we can go around that. We can go around that one. A lot of missing data. Go around this one. Pretty much bring our moisture up and then back around. Let me get to a different color just for the so you guys can see it. So we get around all of these black plots. That's all significant moisture, so you can pretty much take it out to there. We don't know. We got high pressure, we know, over the Atlantic. You can see that down there. And then this is maybe some clearing in this area with that ridging. Maybe not. We still got moisture. Let's just leave it there. Bring it all the way around. Any of the dots that are clear, we're going to have to go around those. So maybe there is a whole little clearing right there. And then all of this other stuff is pretty much 60% humidity or more. Significant cloud cover, moisture, means it's saturated. Basically, the upper number is your temperature. So we got 6 degrees Celsius, 5 degrees Celsius, 6 degrees. And then that lower number is 1 degree. That's your dew point depression. So the dew point depression is the difference between the temperature and the dew point. So if we have 5 degrees temperature, we have 3 degree dew point. The dew point temperature is always lower than the temperature. So just take 5 minus 2, got 3, and then that shows significant moisture. Well, now this isn't putting the moisture there. It should, but sometimes this data is a humidity that's downloaded as a separate data than it is these plots. So it kind of separates the two. A lot of times you get lucky, like it's picking up these. I mean, it is doing a fairly decent job at placing those on top of each other, and them still being significant moisture where those need to be. So now this station plot right there showing a 5 degree and then a 12 degree dew point depression. There's a 12 degrees difference, so that's a pretty widespread. That probably take that with a grain of salt. That might be in might have just been some fluke data or something, but that's okay. So if we looked at our low pressure system on the surface, let's go back real quick to, I'm not going to go all the way to the surface. I'm going to pull up the just overlay the surface right over top of this. Those surface plots, the surface system. So now we got our low pressure system over the Great Lakes region, right over there, right around over New York. And now if you go up to the 850, let me remove that real quick. So now we had, let me get rid of this, go back to red. We had low, and now we see our contour almost closed there. I don't see the easterly flow to prove it closed, but it's almost closed. We got pretty good flow right here, so almost closed right there. So now we place that low. Get rid of that real quick. We had the surface low, then we're stacking back, kind of rotating right there. So now we have that stack on the low pressure system, and then we had our front coming down, and then if we go to an upper front, we'd want to place it. There's a wind shift. There's a wind shift. So now we have an upper front, and that supports the surface front. And actually, that was back just a little bit. So now we can look at this and say, what is how far back apart are these, and to try to determine the slope of that front. So as we take this high pressure system and the surface high, as it ridges, you got the cold front, the leading edge of that cold air mass pushing out of the north. Then you have the leading edge of that cold front on the surface. Now in the upper levels, you have another front behind that. So that's the next level up on that dome. Now if we go to the 700, and we can still see the wind shift, temperature differences, we have another upper front that we know, this high pressure system is ridging all the way up into the upper levels. So now we have an even further upper front. And then once you get past 700 to 500 millibar, look about 18,000 feet or so, that's when you'll most likely just have a trough in the upper levels. So those high pressure systems, if they typically don't reach that high in the upper levels. You'll get the front, and then you'll have an upper trough supporting from there. Then very rarely, another thing you'll have, like pretty intense low pressure system. You got a low. You get the red here. You got a low at the surface. Stack this back. We said we had a low. Stacked back. Now, if we go up to the 700, have another low. We get rid of that. So we got another low, possibly, or yes, they don't want to write. Okay, or you have a trough. So if you have the upper front, you probably got a closed low. If you have a trough, then you just have an upper level trough supporting that front. And then you have another low or another trough in the upper levels from there. So then that one supports the next level up. Now you have a pretty intense low pressure system stacking back like that. And that's you got the tilt of the storm, that cyclone, and that's developing a really pretty strong cold front coming through from that high. So now you get the steep slope. So we have a low at the surface, and then got the front, and then at the 850 got the front, and then at the 700 got the front. Now we know we got a pretty steep slope. Now you're going to see most of your weather at and ahead of that front. That's just this slope of this high is so steep that as the high pressure is pushing through, it's just plowing all of that moisture, causing that lift up the leading edge of that high pressure system, and then just creating a big strong line, kind of like what we're seeing there, and just plowing it along, and you get them big long, just intense weather, fast moving squall lines that'll rush through. Typically that's a fast moving front. So now it's an inactive front is the terminology for that. You got a front, all the weather's at and ahead of the front is a inactive front. That means it's not behind it. So you got, if you had a front and all the weather is behind that front, now you have a shallow slope. So the high pressure system is pushing through. Now, maybe have an upper front a little bit further back, and now you got all that moisture pushing up that shallow slope, and then that's giving all of your lift at the point where any weather to develop at this level and not down here, because your slope is so shallow that you don't hit your lifting condensation or convection level there at the front at the leading edge of that front. It has to come back and up higher on the shallow slope front to be able to reach that condensation level. So now all your weather's at and behind the front. So now you got your cold front, weather at and behind it. These are typically shallow highs and slow moving. They're just slowly moving through. The lift hits the condensation level, and then you got it's an active cold front. All the weather's behind the front. Okay. So we know we had, get back in here. the drawing, we got the low. We said we could stack the low there. We had our front, then we can stack our front back, so we have an upper front. So that's pretty decent. And then we still have the contours, upper level contours, troughing. See all that troughing. And then the isotherms crossing those contours. Now we have cold air advection in the upper levels as a high pressure system still moving through. It's that high pressure system's behind this, pretty low. I mean, it's got a trough there, but the high pressure system behind that upper front. So we still got that cold air advection pushing in from the north. Alright, so alright, had to get a drink. So we got let's get back. Let's go up to 700. So we're significant moisture. Let's do this one more time. Just review our. We had the lows, we had the stacked lows, we had the upper front. Significant moisture all over the eastern half of the United States. Just stick with that for now. High pressure system, check that out on the west coast. We still have cold air advection out of the north throughout the central U.S. Alright, so get out of here. Let's go to 700. We'll run that. Okay, so now we can see let's let this finish building here. Alright, still got come on, let's see here. Nope, not what I want to do. Okay. There's a shift right there. So I'd say the troughing is up this way. We might need to rebuild this chart and do a balanced height. Sometimes these computers get they start analyzing this data. Kind of wants to smooth things out, so get a little bit more level there. We'll go through this for a minute and then see if we have to do that. But right now we still got the contours. Let's go with that. We had the low over New York, stacking back over the Great Lakes region, and then if we had to stack it back again, this is pretty far up there, but I'd almost say no, we don't have another low. Probably more have a troughing. So if we go analyze that, we're going to have to look at where's our shifting at. So there's a wind out of the north. There's a shift right there, pretty strong. Right there's one. One's out of the north. So now we got troughing. Now upper level trough at 700 millibars. This is about 10,000 feet. So pretty strong major shortwave because you got the isobars. And this is getting messy. And you have the contours or the isotherms. You have the contours and then the isotherms still crossing each other. Alright, so now we still have thermal advection, cold air advection out of the north. Major shortwave, unstable wave pushing through, supporting that surface low, which is up here, and giving us any kind of significant weather, especially with the moisture present. We have dew point depressions, 5 or less, colored in. So we still have the significant moisture. We have moisture all the way up into the upper levels, so that's why, like Ohio, actually starting to dry out right there. You got a dew point depression of 8. So we're drying out in that area. But as this moves to the east, we still got moisture pushing back in. So as these balloons are let go, 8 in the morning, 8 at night, then we got that data that's clear at that time, but in a couple hours we still could have the moisture shifted to the east. All right, so still got cloudiness out there. If you look at that picture, southwest Ohio, we're still overcast. And then even if we're, which actually that video, when this there was a little bit of clearing that came through and you've seen blue skies in the upper levels. So 10,000 feet, possibly a no moisture at 10,000 feet. We've seen blue skies, so nothing that high, but you still have moisture at 5,000 feet, 7,000 feet. You got significant moisture and still have all this precip. So let's call this major shortwave for upper level support. And then we'll go to the 500. Still got significant moisture. We don't have the low. A little bit of ridging through here. If you have to look at those winds, there's a pretty good wind shift right there. So this might be an little upper level trough right there. Let's see what we got going on. Let's see, through the mountains. We're well above the mountains here, so winds are out of the west, winds are out of the northwest, winds are out of the southwest. Some low level or upper level convergence right there. So we had that low pressure system kind of look like it was trying to develop right just west of the Four Corners area. So try to support that. There's a trough. A little bit of shifting there, not a lot. Temperatures of 4 and 1, -3, -5. So not really seeing maybe some minor short waves or something there. We'll go up to 500, go up to 300. Maybe we just got a little trough right here that's reflecting from the upper levels. So once we get in the upper levels, maybe we'll start seeing a little bit more significant feature on that. I mean, you go technically go this way, you got a ridge right here, you got a trough. So, definitely a wind shift right there, and definitely a wind shift right there. So, ridging to a trough. So we'll see what feature takes control in the upper levels there. Keep it on that. This down here, don't worry about that. That's like lack of data down there in Mexico. So the computer just kind of generates something, almost look like a hurricane if you want it to be. But that's high pressure, so going to 3210, 3240. That's going into a high pressure, but definitely not there. Let's go with let's go to another level up. Go up to 500. We're going up to about 18,000 feet. All right. All right, so let these station plots get on here. We got that significant moisture right around the plains. We got that could be a push to the east. That's all the moisture. Maybe we're seeing pushing up to 50,000 feet over Alabama. So, like I said, as these charts progress, this could be 8 o'clock in the morning. It's not 8 o'clock at night Eastern time. So this will be 8 a.m. This is old data. So we're coming up on 11 hours. almost 12 hours late on this data, so all this stuff shifting to the east. You got to take that with a grain of salt when you're analyzing these charts. These charts are only good; they're real good for in the mornings. You can forecast throughout the day, move these systems, prog your features, and find out where. Give it an estimate of where they're going to be 12 hours from now, 6 hours from now. So that way, when you get to this time of day, before you get that next set of charts, that you have some pretty efficient data to go by. So just something to keep in mind. I do upload these charts on my website, Meteorology101.com. You can just, in the right-hand sidebar, you can go down to the surface and upper air charts. And I post quite a few charts there. Try to keep up on them every day. Sometimes I don't, but if I get more viewers and get more likes and people sharing my videos, get this YouTube channel built, I'll definitely keep up on that, and we'll just keep building from here. So 500 millibar chart, we're at 18,289 feet, 5,576 meters. All right, so whatever you want to do, meters or feet, pretty much, like I said, significant moisture, dew point depressions, 5 or less, all through the south central U.S. We had all that moisture to the northwest over the mountain range, and we had pretty much on the initial radar we showed. First thing was a bunch of scattered rain showers, but scattered rain showers, snow showers. Most of it was rain today. It looked like through the mountain areas, the upper elevations, and then we had that line all the way from, well, not that far up, but Maryland all the way down North Carolina, South Carolina, into Georgia, Alabama, Mississippi. So have that line, and then got all this moisture. So like I said, this could be pushed east. So we're looking at, we had that low pressure system over New York, stacking back over the Great Lakes region to a upper level trough. Now we got another upper level trough showing support here for that system. So that system's all one stacked system into the upper levels, got the tilt on that system. It's a well-developed system. That's what that means. So be even worse if you had, a close low, surface 850, close low at 700, close low at 500. Then you're getting a pretty intense system, and then keeping that thermal advection all the way up. That is an intense system. What I look for is like we had the storm of the century, was 1993. We had low pressure in the Gulf, just sucked up all that moisture and then just pushed to the northeast, and then we had just snowfall, tons and tons of snow. So, all right, here's our feature for the upper levels here. We have the surface low, we had another low, we had a trough. All right, so we go back a little bit further on this one, we can start analyzing another trough. If you look at, kind of looking at a wind shift, but I'm looking at that wind out the southwest. This is more westerly, so we got a shift there, got a shift here. Getting a little low on data. We got still a little bit of a shifting going there. I mean, you could almost put a trough right there. Got shifting right there, so let's not call it a trough. We got minor shortwave, maybe. So we go like this. Let's go. Contours, troughing, and then we go over here to alright, thermal advection. What do we got for thermal advection? That's what we're looking for the upper levels. Call these things either major, minor, short waves, long waves. Short wave, tight, tight troughing. Long wave, long troughing. So many degrees of latitude is what that's based on. I don't have the details right this second, but pretty much a major shortwave. And other things like major shortwave would be, does it have thermal advection? All right, so in the upper levels there is no friction, so the winds will follow the contours more parallel. See how they're going right along with the contours? There's nothing to stop them to create that backing to, slowing to any friction, to slowing the back the winds. If they go over water and they speed, they'll speed and veer. So winds always speed and veer, or they slow and back. So what I mean by that is, so this wind right here, out of the southwest, if this was to slow and back, it's at 25 knots. Okay. If that was to slow and back, then we could say it drops to 20 knots because of friction. But this is upper level, so this is just for educational purposes. All right. Then that wind to back would be more of a southerly wind. Now, it's not going to go 45 degrees, probably just a few degrees, 10 degrees or so. Now your wind's backing, and it went from 25 knots to 20, so it slowed down. So now you have backing and slowing. All right, veering, then it would go more clockwise, in the clockwise direction for the direction. For the from direction, because these winds are pointing, just put an arrow on the end of that, on the end of this, the flag there, and then that's the direction of the winds. So they're from that direction. So if you went veering, this wind would be more westerly, and they would speed, and then it would be about 30 knots. So, I mean, not always 5 knot difference, but, you know, they will veer and speed as they like go over water with less friction. This is on the surface. If they go over water, now they lose that friction from the land, so then they veer and then they speed up. So if they come on shore, they hit that land, and they're going to slow and they're going to back. All right, just a quick lesson there. So back to our points, we got the trough, contours crossing. We still have cold air advection out of the north. We're getting a little more parallel up in this area, though. See these isotherms becoming more parallel. That system is starting to fill from in the upper levels. So we're getting, the trough starting to weaken a little bit. So we got, not a whole lot of thermal advection there. It's all kind of behind that trough is where our thermal advection is. So cold air advection in the back. So now the high pressure is kind of, you got this ridging right through there. So that's your high pressure just showing a little bit of a ridge in the upper levels, and the low pressure system showing that troughing in the upper levels and still have a little bit of thermal advection to continue with any significant weather that you would have. You'd have a pretty much a major short wave. This thing's starting to weaken pretty good. So now the intensity of that storm would start to weaken also. So now look at these contours. They're crossing right there, almost crossing right here, crossing right there, crossing there, crossing there. So there's your cold air advection. That's the almost be like the high pressure, but you got lower heights here because your high pressure isn't going to ridge all the way up into the upper levels. So you got lower heights because it causes lower heights in the upper levels with cold air, because that cold air wants to sink. So you got lower heights, cold air, and then your slope of your high pressure system on the surface, upper front trough, that would be your upper level support, would be that troughing back there. So now you got your lower heights because of the high pressure on the surface and behind that front. Okay, so this is, we got 500 millibars. We'll run another chart at the 500 millibar level. We'll do the vorticity, and that's going to show areas of upper level divergence, and throughout the middle, starting into the upper levels, you get the upper level divergence, and you get that's your exhaust for those thunderstorms. So if you have that low pressure system, upper level divergence, anything on the surface, the cold front comes through, lifts it, hits its level of free convection, goes up, you have upper level divergence, you're going to have a pretty intense thunderstorm. That's why those thunderstorms can reach 30, 40, 50,000 feet. So let's go ahead and run a Vorticity chart. All right. Okay, let me get one more thing on this chart, and that is going to be the vorticity itself. So we can see it colors in the vorticity advection, but if we actually look at the hold on a second. It gets to shows where the vorticity is, so we can see why it colors in the that vorticity advection in those areas. All right. Okay, so now try to get this thing to react here. Come on. All right, that's a negative vorticity right there. We have that would be negative vorticity advection. That's all the dark stuff. So the winds are blowing this way with the contours. Positive from the behind that. Here's an X. That's positive vorticity. But we don't have any major advection. We got the positive vorticity right here, but there's nothing, no next level in those areas way out here, and that's not going to be strong enough to be in that area, so it just puts a weak spot. So that's pretty accurate for that. So upper level divergence we don't have. We have negative vorticity. Like I said, this data is pretty old, so as this moves east, we should have more positive over here, but this probably became more intense as it moved to the east, and then given that upper level support there. So I didn't really see it at the 500 millibar level for any winds that were, diverging. So indicating of upper level divergence on the with the balloon data. So pretty weak chart here. This is pretty weak. We got that low pressure system that was over New York, and then that was stacking back, and that's all into looks like negative vorticity. We got a lot of positive up to the front, but up to the north of that, but then we had that trough to the back of that. That's at the 500 millibar level. So not impressed with this at all. So we're just going to get out of here and go to the next chart. Let's go up to a 300. We'll pull a jet stream. We'll pull a 300 millibar moisture. See if we got moisture at 30,000 feet, and then we'll pull a 300 millibar jet stream and see what we got from there. All right. Okay, we still have significant moisture at 30,000 feet over the central plains. So if we look at that, we can go to that pushing to the east. Get rid of that. So that pushing to the east, then we have all that moisture right there when we need it for those severe storms. And if we have a little cyclone developing right there, then pretty much have everything we need for the moisture and stability and lift. And we got those severe thunderstorms, tornadoes over Alabama. So this wind directions are just kind of all over the place here. There's no friction to mess with us. We got pretty much winds going along with the contours except for that one. That one's just shooting up to the north. So kind of hanging in there along with the contours. Now you look at the 300. Now we're pretty much, these isotherms are parallel with the contours. So now our upper level support is pretty much gone for that low pressure system on the surface, and really no advection right there to really worry about. Maybe some weak advection right there. Let's see. That one blowing into this one and giving a little bit of weak advection right in that area. But other than that, nothing significant to worry about. Let's go to the jet stream and see what we have for see our jet placement based on that surface low, and get an idea of what we're working with for upper level support from the jet stream. Alright, we are, for some reason, we are not at 300 millibars. We're 500. Let me get back over here. So I need to go back and run another chart because we didn't get our 300 pulled for our moisture. We've had that moisture from 500 millibars we were showing in the Central Plains. See if there's anything at 300. That's moved to the north, so that moved to the east, and that would be higher clouds over the Ohio Valley region. There's a long wave trough, and looks like alright, so we get back. Okay, we got weak thermal advection. Really nothing there. Significant moisture. That probably pushed to the eastward. Like I said, we're about 12 hours almost behind now on this. So wind shift here. Troughing. We can see that rotation there. We definitely got troughing in that area. And I didn't really see anything for the four corners, so no upper level features supporting all that stuff at 500 millibars or 300 or 700 millibars. We had that little bit of troughing and ridging, so kind of over the mountain area. Nothing there to really support much of that. We do have that trough moving all the way down through here, though. You can see that shift, the wind shifts. So we have that troughing in the back in that area. So weak thermal advection. Got some going on there, not a whole lot. And then, like I said, this moisture, significant moisture, is probably moved to the east. Same thing with that trough, it's probably moved a little to the east. So you could kind of shift this thing forward, and based on the 500 millibar wind speed, 700 millibar wind speeds, you can base your frontal surface front speeds, how fast that front's moving, based on a couple of those. I covered that in some other videos. We'll get more into the educational side of this here a little bit later. So let me go back to, let's pull the jet stream this time. Get rid of this. Let me go clear that chart. Alright, 300 millibar jet. Got some low clouds moving through southwest Ohio. It's look like that some little fractus clouds that are from the just remnants from that rain that came through. Alright, so we got a long wave trough in this jet stream, so let's get our contours, isotherms, and our plots. Alright, so get back to drawing mode and see what we're working with now. Okay, long wave trough. We can see troughing all through here. That's your long wave. Pretty tight right through here, though. But we don't have any, all of our isotherms are kind of parallel. We do have a little bit of crossing right here, so a little bit of cold air advection right there. So that's the upper level support for that surface system, all the way stacked all the way back. So a little bit of ridging near the four corners area. Jet max. Got a jet max here. So, and then a little jet max right there. So here's our, if we had that unstable wave, all right, we had the low frontal system. Now we got our jet max, our jet support right there for that low pressure system with the front, that surface front, and like I said, we got our jet support, and then we got this cutting off right here. So it's like this is almost trying to make that turn and become a cutoff low. If this does, then you can get a cutoff low there or right there around the four corners area. Typically where it happens, right there around the four corners, you get this jet can't make that turn, so it just goes. It just overshoots this and leaves a jet max right here around that four corners area, and then a low pressure system develops and then just sits there and spins. Now that can be kicked off by a major short wave comes along, runs into that low, kicks it off, becomes another low pressure system, and then moves off to the northeast, follows the jet up as that jet overshoots that. So that'd be your steering flow, and then brings that low pressure system up. Now you can get a whole nother system develop. So you think you got high pressure coming down on the surface, you got your cold front passing through. Once your cold front passes, everything pushes through, the high pressure builds in, then you got clearing skies. Okay, unless you get a low pressure system develop over the four corners area, we got the jet stream that shoots off. Now leaves that finger, and then a kicker comes along, kicks that low off of there, and then now you got another low pressure system that developed, moves to the northeast, picks up all that other moisture remnants from that other system, that frontal boundary it moved through, and then becomes more unstable, and then upper level low, high pressure on the surface, and get your upper level low, and then any precipitation, moisture associated with that low falls through the high, and then you'll have just the upper level storm, elevated storms. So that can happen too. So, all right, we'll go one more level up to the 250, and then that's going to probably give us a little bit better look at these jet maxes, and then other than that, ain't much more to talk about. We'll go back to the radar. See what our warnings are showing. Severe weather. No tornadoes unless I missed one, but I didn't see anything pop up. We'll go back to we'll go up to the 250. Pull our jet. Definitely gets that curvature right there, so looks like definitely maybe a cutoff could become a cutoff low if that just decides it's just going to overshoot that, and then leave it low, leave it jet max down there. And another thing we could have here, this isn't really depicted very well, is a let me get the pressure up real quick, is a subtropical jet. Let me get back. Let me build this chart here first, and we'll talk about some of this stuff. Okay, let me get plots going. Alright, now, long wave. Now, if this thing overshoots, we could get a cutoff low, or we could just have a finger of the subtropical jet pushing through, and then the polar front coming down, and then converging with that. So that's a possibility what we could have going on here too. But now we got some ridging going on here, so it's almost like like a subtropical jet polar front. Get the jet max there. Jet max there. Kind of a jet max there with the subtropical jet stream. So your jet stream is caused by a north-south temperature gradient. So temperature. Now this is one level. You're gonna need more levels than this to analyze a jet in a 3D to get an idea. We got a cold core there, 52 degrees, and then here's another 52 isotherm. So if we take, that's actually coming down right there. That one's up there. This is right there. So now you got divergence there. Well, that's pretty cool to see here. That would be divergence there because if that follows the contours, then this is coming out. More of a convergence down here. That's what the thermals. We're kind of analyzing across each other here. So, we still got some cold air advection to the north there, though, over North Dakota. Upper level support for that system, and maybe some ridging right there. Let's see. I mean, we're pushing all the way up, so I'm not too sure. We're coming down, pushing up. So we got a pretty deep trough. That's what we're working with right there. And then we got the ridging, pretty strong ridging in that area. So bring that one up. So there's the ridge, trough. So I'd say that's almost one jet stream. Alright, so we have jet support for our low, surface low. Front. Jet stream. There's our support for that low pressure system. So we have everything we need. Jet stream blowing over top of that low, sucking the mass out of it, creating that, giving it a more intense low pressure system on the surface, and then support all the way up in the upper levels. So we're pretty good on that low pressure system. That's a pretty good analysis for a low. I got better ones. Look at some other videos. We get pretty deep with a closed low all the way up, and they get pretty intense. So this one's not there, but do have upper level support. Still have thermal advection in the upper levels. Just one small area that's weak. But hey, that's get rid of that stuff. All right, that's pretty much it. 200 millibars. I'll download these charts. I'll save them. Upload them to Meteorology101.com. I'll put a link in the description to the charts, and then you can follow that whenever you want. If you have any questions, put them in the comments. Any comments, put them in the comments. I don't care, good, bad, whatever. Thumbs up, thumbs down. Like my channel, subscribe. Help me build this thing, and I'll keep these videos coming. So let's go look at the radar real quick, and then we'll call it quits. Let's go see what give you a better view here. So alright, so we got our line moving through Mississippi. Still several severe thunderstorms. Let me get my window, my warnings window. Oh, we do have a tornado just popped up in Kentucky. Alright, so Central Kentucky, let's see here. Springfield, Loretto. This is Marion and Washington counties in Kentucky. Let me get my... Let me download this loop. Okay, so now we definitely got a little hook echo going on there. Let me see what we got for a cross section real quick, right across that. Pretty good upper level upward vertical motion there. We got a tilt on the storm. I mean, you could say, yeah, if there was a tornado there, that'd be pretty much all the way to the surface. That higher reflectivity's pushing all the way up to almost 20,000 feet. I mean, definitely probably going to see rotation in this storm. They probably did justify throwing that tornado warning out there. Let's go to base velocity and see what happens here real quick. This is on a cross section, so Let's kind of see how that turns out. There's definitely rotation in the up to 10,000 feet on that one too, so that's pretty good. Pretty intense right there. So nice little cell developed in Kentucky for us. Let me go to I got the hook echo. You got hail right in that area, and then if we go watch that hail icon, if we go in the upper elevations, you can see now where those high reflectivities start coming over that hail. That's falling down to the surface through a little bit clearer area through that hook echo. So let me get back to the surface and then do a base velocity. Now you can definitely see the rotation in that storm. You always look for your radar. Where's your radar at? Right here to the northwest. And then you want to look at the red's going out, green's coming in, so you definitely got rotation in that area. There's probably some rotation up here too, so looking at the reflectivities, what do we got up there? So here's your hook echo to the southwest quadrant of that cell, so that's where your tornado is going to happen. So that's why our tornado warning's there, and then they covered enough area for that to move through, and then maybe push out of that area, and then keep it up active long enough to stay in effect. We got 25 moving 25 miles per hour to the east, and it's radar indicated rotation, and this is valid until, let's see here, 8:45 p.m. Eastern time. It's about another 24 minutes. So that's a pretty good little storm right there. Let's go. Let's get this thing centered, and let's do a volume scan on that and see where we're at. All right, here's the lower reflectivities outer shell of that storm. It's pushing all the way up to 30,000 feet. And then here is the core, and then we can isolate this stuff all the way down to 50 dBz. Now we have our upper level higher reflectivities up to 20,000 feet. Got the tilt of the storm, updraft, and now let's do this. Go to just some small outlines of the lower reflectivities. Give us an idea where that whole thing's built up at. So that's pretty much it. Let's go with the rotation. Now we got rotation all the way up to almost 20,000 feet also. Pretty strong in this lower levels right here. Right about 12,000 feet and below. And that could easily reach the surface as a vortex if it had to. So it continues to intensify. So we're rotating pretty good on that storm. So rightfully so, calling the warning on that. If you're in that area, you probably drop on a little bit of hail and probably take cover. Let's see, this is north of Loretto. It's Marion and Washington counties, Kentucky. Nice little hook echo right there. So here's a little tighter shot on that thing. Like I said, right here. Alright, looks pretty good. Let's go see what we got here. Okay, KLVX, Louisville, Kentucky. Let me save this radar here. Alright, let me go. Do that scan, save this thing. keep these volume scans just to keep some history, keep some archives of the stuff. So. All right. We don't want to do that. All right. Okay, you're not gonna let me. Let's go get out of this. Pull up another radar. I'm gonna pull up a composite reflectivity. I think you might be able to see it. Let me go here to Alright, let me see. Okay, I'm going to say my radar shots. Okay, there's a composite reflectivity showing the higher DBZs, pushing about 62.5 DBZs. You got that little hook echo, so sometimes you turn that smoothing off and you can get a little bit more data out of that. So this does a pretty good job as far as smoothing it out and still keeping those reflectivities right here on this cell, but can't do any cross sections or anything like that on this program. This is just composite reflectivity. That's basically takes every layer of the radar and puts them all together on one screen so you can see the complete storm as it's moving. So there's the advantages of that is if you have something in the upper levels of the radar and you're only looking at a base reflectivity, you're not going to see those upper levels. That's why you'll see those hail icons over a bare area on the radar, like an empty area. But in the composite reflectivity, you're not going to see that because you have the complete every elevation of the radar on one screen. So now it gets a little more cluttered, gives you a little bit of reality on the storm, but a little bit of false information too. And you can't break that storm down to how it's actually structured. So you think that hey, the cell's reaching all the way out, and actually it's elevated in one area, and then where it comes down to the base reflectivity to the surface is in a different area. So you want that base reflectivity. You want to see what's on the surface. That's what's going to be, like especially on these tornadoes, you do any spotting or storm chasing. You want that base reflectivity. You're going to want to see what's on that surface to see your hook echoes, where they are, and where you can go into the bear's cage. So we'll explain all that later. But let me get over here to right there into the hook echo. So now we're seeing a hook echo way back here. Let's go back over there to the base reflectivity real quick, and get rid of that. Go open this one. Now we're seeing a hook echo way up in here. So now that's the difference. You're looking at there's a hook back there. There's some hail, and then you got rotation right in these areas. So let's go look at this. Right there's your rotation. That's why the warning's here and not back here. I mean, there is a little bit of rotation right there, it looks like. So actually this radar, let me get my pointer back on here. Radar's to the northwest. So we go into this storm. Now you got the green in, red out, green in, red out. You don't have any much red out right here to give you that counterclockwise rotation. But you do over here in the warning area. So now you definitely got the gate-to-gate shear, and you got the, that definitely indication of rotation right there. So let's go with 51 knots right next to 51 knots right there. So you're about 100, 101, 102 knots of wind shear right here. So trying to see this data if we got. Let's go in the upper levels. Let's see where we're at here. See, we got rotation, 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 for rotation. Now we really got the gate-to-gate shear going on right there. We got. It's a 51 knot total wind. It looks like. So hail. There's a hail, full half-inch hail just popped up in the center of that. Like I said, you go in the upper levels. Now we're losing our rotation, way in the upper levels, and then we lose that velocity altogether when we go way up into the upper levels of the radar. So when you take that composite reflectivity, here's your base reflectivity. This is one layer. So we can get rid of the smoothing. You get a little bit more data and the pixels. You can actually pinpoint the tail of the tornado or the vortex of the tornado, and when you get rid of the smoothing kind of just kind of blends everything together and make it a nicer looking picture. But you can lose some data doing that. So, but here's your base reflectivity. Go over to the composite reflectivity. So let's go back and forth here. You can see the difference. Actually, I'm zoomed in on one too much. Let me go back, get out of this, and we'll try to get these lined up to each other here. Go zoom in. Alright, so here. Now, still moving a little bit, but we're got, just because of the way the screen's cropped, but you can see the difference between the base reflectivity, composite reflectivity. So we don't even see the higher reflectivities. We get on the base reflectivity, we don't see that. On the composite, you can see there's higher reflectivities, and that's pretty much where your hail is going to be. We're going to have, well, there we just had the hail pop up in that area. Let me go right there. So the hail is going to be right around where those higher reflectivities are, because that's the hail creating that higher reflectivity. All right, let's go back to get rid of that one, and get on the same page. We'll go to I don't see the hail there on this this radar is not depicting it, so let's go. There's one in the center of the screen. So it's hanging out there. It's right there. So now if we go to the upper levels, now you can see that purple pop up, and then we get to the higher reflectivities. So now that's where our hail is, and there's in the center of that. So, all right. I'm going to go ahead and end that video here. We got Washington County, Kentucky. Several severe thunderstorms. There's a tornado in Kentucky and flash flood in Georgia, Kentucky, Alabama. And then we also have those special marine warnings all along the East Coast. So severe thunderstorms along that East Coast also. But that's pretty much it for tonight. This has been a pretty long video, so I'm going to call it quits. And I want to say thanks for watching. Hit the thumbs up. Like I said, we're going to get into some more weather educational videos. I'll talk about a lot of weather details. Might be a lot to absorb right now. A little over people's heads. Terminology, stuff like that. So we're going to get back into a little bit of education and go from there. Thanks for watching, and like my channel, share my channel,